Do 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 do. Greetings, Internet Scholars. This is your Jesse Styles, and welcome to a very special episode of Twisted Signals. Today we are going to be looking at creating patches that do time shifting, otherwise known as delay lines. And we're going to look at how to do this to audio signals as well as video signals in Macs. We're going to look at adding feedback to delay lines to create perpetuating echo systems, and then adding other forms of processing that will cascade in interesting ways once we've established delay lines and feedback systems. So let's start by looking at some basic stuff. We're going to look at how to add and scale audio signals first. So here are three different audio signals. We've got these three sine wave generators here, and they're all connected together to this object. So to add together these three signals, these three audio signals, it's as simple as just connecting them to the same audio object. And then Max automatically is summing together these three audio signals. So that's pretty easy with audio. You just connect them together. To scale these signals together, we're using this object, which is an audio rate multiplier. We've got three signals, and we're multiplying by 1/3. And that keeps this audio signal within this range of 1 to -1. That is the normal range of digital audio. We kind of arbitrarily say that digital audio is going to be between these amplitude ranges of 1 to -1. Now, the computer, we could represent audio signals that go outside of those boundaries. Like that. But when we do, we get this form of distortion that you just heard called clipping. Clipping is what happens when an audio signal goes outside of that range of 1 to -1. So this clip object is showing us on the graph that our nice smooth waveform, when it gets clipped, we're chopping off the top and the bottom of it. And this results in distortion, which, if you wanted to use that intentionally as an artistic effect, go ahead and do that. But if you're clipping by accident, you're just going to be introducing distortion to your audio signal for no reason. Okay, so that's just adding and scaling audio signals. Let's look at how to shift them in time. These two objects are the objects we use to create an audio delay line in Max, tap in and tap out. When these two things are combined together, we create a delay buffer. So tap in tilde has an argument which is going to be the size of that buffer in milliseconds. So this is 10,000 milliseconds, which is 10 seconds. So we've got a delay buffer here that can be as long as 10 seconds, and we connect it with a patch cord to a tap out tilde. And tap out tilde has an argument which is going to be the initial delay line time for this delay line. So let's turn on audio processing in this window. Okay, so we can change the delay time by sending a different number to tap out tilde, and we are going to be time shifting this original signal by different amounts of milliseconds. And this would be the difference equation for a system like this. We have our input signal, which is x of n, and then x of n minus d is that same signal somewhere backwards in time. So you subtract this delay interval, and that gives you your delayed signal. And then we can scale the original and the delayed signal by some amount, which we are calling the feed forward coefficient, written as B. Here we are introducing feedback to a system. So we have our original signal, we're listening to that in the left speaker, and then the right speaker, we're hearing the output of our delay line. This is the same kind of system. We've got tap in with a maximum value, tap out with an initial value. We can change it using this number. You'll see here we are using a different object to change the delay time. Line tilde generates audio ramps. Let's look at the help file for it. So let's turn on audio here. You can send line tilde numbers and it will immediately jump to those values. If you send it a list, it's going to interpret that list as a target and then a ramp time. And let's remember, of course, that in Max, when you use a comma in the middle of a message box, it breaks your message into two different messages. Let's actually quickly demonstrate that. So here's a message box that says hello, comma, world, and let's print the output. Excuse me. Hello, and then world. So those are two different messages. They're broken up by that comma. So in this help patch, this message box is actually two different messages. So the first message just says this. It's just a message that says 0. So line tilde immediately goes to 0 because this is just one message. And then the next message says this, 1, 2000. So in this case, because it's a list, 1 is the target, and then 2000 is the ramp time. So over the course of 2000 milliseconds, line tilde ramps up to that. So this message box, when we send it, it sets it to 0 immediately. That's the first message. And then the second message ramps it to 1 over the course of 2 seconds. And then here is a longer list. So this is going to be target, ramp, target, ramp. It's going to go immediately to 0 and then ramp to 1 over 2000 milliseconds. And let's actually modify this. We'll make the second part of the ramp very slow. So it quickly ramps up to 1 and then very slowly ramps down to 0. So, no, don't save. Don't save. Here, our example, we're using the pack object to pack together two different things. And let's just print the output. And let's look at our Max console. You can see the first element of this list is getting replaced by the number that we send to the left inlet. And then because we're not sending anything to the right inlet, the second element of the list is the same. It just stays to this initial argument. So this is generating a list that we're sending to line tilde, where the first element is the target and the second is this ramp time, which in this case is 100 milliseconds. So let's listen to what happens when we change the delay time using this audio rate ramp. Audio on. So you can hear there's a little bit of a pitch slide when we change the delay time. It's as if we had like a record, and in order for us to quickly move to a different part of the delay buffer or slow down and get further backwards in the delay buffer, we have to make the record speed up or slow down to get to that point in time. So you get this kind of like record scratching sound effect, which this is used a lot in audio processing when you want to create these kind of interesting pitch effects with a delay buffer. And if we introduce feedback into this, we can exaggerate or propagate those interesting sound designy things that happen when we get those pitch shifts. So here is where we're going to introduce feedback. The output of our delay network, it's going to go into the speakers. We're going to hear it. And then we're also taking that audio signal and running it into this volume fader. And if we bring the volume up, the output of our system is going to go back into the input stage, and that creates feedback. So let's listen to this with feedback. So in the right channel of our audio, you can hear these echoes building up. And because there's feedback, these pitch effects are going to get exaggerated and propagate over a long period of time because we hear it once and then we time shift it and send it back into our delay line. So we're hearing these things over and over and over again, and we can take a pitch shifted version of the signal and pitch shift that, and we'll get a sort of cascading pitchy effect when we do that. So if we wanted to write this out as a difference equation, it would look like this slightly more complicated equation where our output is our input, and we can scale that by our feed forward coefficient plus the delayed signal, so x of n minus d, which could be scaled by a feed forward coefficient. And then we take the output, which is y of n minus d, and add that back in as well. And we can scale that by our feedback coefficient. So this red part of our equation represents the feedback side of this. This is just showing us a demonstration of using multiple tap outs. So here we have one tap in and many tap outs because they're all connected together. They're all referring to that same buffer of audio. And you can tap out the delay line at many different points in time. Okay, so here we've got the delay line, we've got feedback, and we've just added one more piece of processing after the time shift. This is an example of a pitch shifter. We're going to look more at PFFT later this semester. PFFT does frequency domain signal processing. So inside of here, we've got this thing called Gizmo, which can do frequency shifting in the frequency domain. So let's turn on audio in this window. Let's add some feedback to this delay line. We can change the delay time and get those record scratch sound effects. And now we can introduce a transposition factor that will take place after the time shift. So if we doubled all the frequencies, okay, I'm just having fun now. So you can create lots of complex, weird sound worlds using just this simple recipe. We just have a delay line with feedback and one additional piece of processing, this pitch shifter. And what we get is our signal time shifted and then transposed, and then we take that transposed signal and send it back in, where again we're going to time shift it and then transpose the transposed version, and then we'll transpose the double transposed version and then the triple transposed version, and you get this cascading scaled effect of whatever processor is added to here, because we have this feedback process. And because it's kind of spread out over time, you can hear it sort of like slowly build up in an interesting way. And of course, when we're using feedback, you want to just be careful that your feedback doesn't explode. If you set that feedback value too high, it's going to get louder every time it goes through the processor, and then louder than that, and then louder than that, and eventually it'll blow up your loudspeakers and your headphones, and everyone will go deaf, and they will hate you. And we don't want that. That would be bad. Okay, so that is time shifting with audio, and then using feedback to make your delayed signals propagate more over time, and then adding other forms of processing to create cascading processed effects. Let's close this, and no, I don't need to save it. Hey, look, it's me. Let's look at our next patch. All right, adding together two matrices is not as simple as just connecting them together as we're doing on the left side of this patch. So if we want to add together two different video signals, you need to explicitly add them using an object like this. This is jit.expr. I like using this because you can put in many different kinds of mathematical expressions, and you can do it all in one place. So it has this attribute called @expr, where you can type in the expression, and we're saying in of 0 scaled by 0.5 should be added to in of 1, also scaled by the same amount. So we're taking this matrix plus this one. In order to avoid them oversaturating the screen, we scale each of them by 1/2, and then we add them together explicitly. So this is necessary. If we just connect them into the same object, at best what will happen is you'll see them being displayed one at a time. But they won't automatically get added together in the same way that an MSP signal would. Okay, so moving on to an actual time-shifted video signal. This is a little more complicated than the time shifting we did with an audio signal. So I'm going to sort of break down how to build a patch that does this. Okay, in the top left part of this patch, we have jit.grab. Jit.grab is opening up my webcam. Hello, it's me. If you wanted to choose different cameras, you could go in this subpatcher and choose different cameras. And then many of the patches I've used so far in these lectures that are using jitter objects, I've been using this object called jit.world, which makes patching in jitter a lot easier. And one of the things that jit.world also does is it makes certain objects like jit.grab automatically output frames as fast as possible without you having to send bangs explicitly to those objects to request frames over and over and over again. So that's just a kind of like convenience thing that jit.world does for you. This particular patch doesn't have jit.world in it. So if you want to get frames out of jit.grab and you're using a patch that's not using jit.world, you actually need to use an object like this to send bangs to explicitly request those frames one after the other. So QMetro is a version of Metro that we use in jitter patches that achieves the fastest frame rate possible. So you'll see this a lot if you're looking at demonstrations of jitter patches, especially if they're from a version of Max from more than a couple years ago. Jit.world is a relatively new object in the world of Max patching. So that's why this particular patch has a QMetro in it, and other things we've looked at so far do not. All right, let's look at what's actually getting printed out of this jit.grabber. So jit.grab is reporting the name of the matrix inside of which these color values are being stored. And we're just constantly updating those color values every time we get a new frame out of this camera. So it's just this one matrix that has this randomly generated name. And I'm using a send object so that I can receive this signal in different parts of my patches. You can actually trace send and receive objects by double-clicking them. So I double-click this send object, and you can see that I've got 3 different receive objects throughout this patch. You can choose them, and Max will actually highlight for you the different places where they're going, which is convenient. So there they are. And of course, S and R is short for send and receive, and that's handy because send and receive keeps your patches clean, and S and R saves you typing when you're using this object all over the place. So the name of this matrix is being sent here, here, and also down here. And down here, these 2 objects are an object called jit.pWindow, and it just gives you a window that you can embed in your patcher to look at jitter matrices. So that can be a handy way to add a kind of monitor inside your jitter patch to see what's happening at different places. Okay, this is the object that builds the delay line. It's called jit.matrixSet. And what it gives you, as the name implies, is a set of matrices. And that's what the first argument to this object is. It's the number of matrices that are contained within this set. So this, let's call it a buffer. This is like a buffer of matrices, and it consists of 400 frames. The other arguments we're giving to matrix set are the typical matrix arguments, where 4 refers to the number of planes. So these are the color planes inside our matrix. That's alpha, red, green, and blue, which combined together give us full color video. Then char refers to the data type inside the matrix. Char is 8-bit data. And then 1280 by 720 refers to the resolution of these matrices. So matrix set, let's just look at the help file for it real quick. You can see that it has these 2 basic messages that make it do its thing. Index is going to be the location to which we're writing matrices, and then output matrix is going to be a written location that you can play back. And then of course we need to actually send it matrices to be written and recalled, so you could just send it this video player, or we could send it other things. Here's my camera, or a different kind of movie file. And in this demo, we're using a counter to wrap around the range of the matrix set. So 0 to 14 gives us the 15 matrices that are stored within here. And then this random number generator is randomly pulling out different parts of this buffer. So at any moment we've stored 15 different frames inside this buffer, and this is playing back those 15 frames in a random order, which gives you this crazy jittery looking delay line. So there's a very jittery version of me. Okay, so if we want to create a fluid looking delay line using matrix set, what we're going to do is, again, we're going to use a counter, which is going to wrap around inside this range of frames that we have. So I'm going to use this number to drive my index. I'm going to write in the matrix that's coming out of my grabber, and then I'm going to output matrices based on this counter. But we're going to do a few specific things here. So If you look closely at what's coming out of this counter, you can see it's actually counting down backwards. And you might wonder why we're doing this in this patch. We're counting down backwards by sending this message to counter dec. Dec makes the counter decrement rather than increment. So if the counter was going up, we could still build a delay line of sorts. So we can use index to write the camera data into the matrix set, starting at 0, going up to 399. And if we want to delay the buffer, we can just write out, let's take this number and subtract 100. And let's just look at that number and use it to output the matrix. You can see when I do this that you're getting an output which is the delayed version of my signal. So why not just do this? This seems to work pretty well. Well, when you do this, if you look at the now versus then, you'll see that the delay line is actually getting broken every now and then. The fluid motion is stopping at certain points in time, and that's happening when this number turns into a negative number. Because we're subtracting from this number, it occasionally goes negative. And there are no like negative frames inside this matrix set. So the trick to make this work is to instead drive the counter backwards. Our delay line we're going to add to that, so a number above this is going to be backwards in time. So this will also work, but you can see it's still broken because we're still going outside the range every now and then, because this number is now going above the range. It's going above 400, and when it goes above 400, there's no frames there, and the delay line gets broken. So we use, the handy modulo object. So we'll say modulo 400. Modulo gives us the remainder. And that's going to force it to wrap around in the range of 0 to 399. Even when we go to 400 and above, modulo gives us the remainder when it's divided by 400, which is always going to be in that range. So now I have a fluid delay line. It's always within the range of 0 to 399. And we could change the size of this delay by adding different numbers to our counter. So we could go as high as 399. And that would give me a delay line that's like the entire size of this matrix set. So this is a 400 frame delay. What that means in terms of time sort of depends on how fast your computer is and what kind of frame rates you're able to achieve. So let's say this computer was running this at 40 frames per second. This would be theoretically a 10-second video delay line. Okay, so that is how we build a video delay line using matrix set. So something that's sort of critical to make this patch work perfectly is this right here. It's an object named T, and it has these 3 arguments, I, B, I. So what's going on here is we're doing some really careful message management. Remember, in Max, objects that have multiple outlets are outputting their message in a specific order, which is right to left. So it's going to be first, second, third, fourth, and last. And then the arguments that we're giving here match these types of messages that Max knows about. So we've got ints, floats, symbols, lists, and bangs. So T is short for trigger. And trigger, when we give it arguments like this, it's going to take our input and output it in different formats. So this is getting outputted as an integer and a bang, and then another integer. And we're doing it in this specific order where it's 1, 2, 3. So what we do is 1 over here, we specify the place inside our matrix set where we want to store a frame. That's the first thing that happens. The next thing that happens is we get a bang. Bang tells this object, zlreg, to output the list that it's holding. And that list is the name of the matrix with our camera data. So remember, we used send and receive to send the name of this matrix over here. And zlreg, this is a list processing object. You can look, it does so many different things, it's almost confusing. But zlreg is a version of ZL that can just take a list and then output it later when you want to receive it. So, like that. So if we send a list into the right inlet, it'll store it, and then when you bang the left inlet, it'll output it. So we are storing the name of this matrix that refers to what's coming out of our camera, and then this bang is outputting it. So we are setting the index for matrix set, and then we're storing this specific matrix at that index. And then the third thing that happens is we're taking this integer, we're offsetting it by some amount, and then we're using it to output the frames that have already been stored. So when we do it in this specific order, 1, 2, 3, we get a perfectly operating video delay line where we can set some delay time and constantly be looking at frames that happened this many frames in the past. Should we save this? Sure, why not? Save, close. Okay, next patch. So here is, this is basically the same patch, except this is using a video file rather than my camera. It's doing all the same things, except I've made it a little bit more compact without all the comments. This is going to be our delay time. So again, we're using a counter. It's counting backwards. This particular counter, this one has 3 arguments. When you give counter 2 arguments, what you get is the range. So that's a counter with a range of 0 to 400. When you give it 3 arguments, so we'll say, actually that should be up to 399. The first argument is the direction. So 0 would be counting up, 1 is counting down, 2 is a palindrome count. So this is saying count down when you get a bang and do it within this range of 0 to 399. So this is actually equivalent to sending it a deck message, as we did in the previous patch. Okay, so we are driving our counter down. We are indexing through the matrix set in the range of 0 to 399. We're storing in this matrix. We're adding something to that and moduloing it, and this is the size of our delay. This is something new that wasn't in the previous patch. So this particular patch, you could load up videos that have different dimensions, and the matrix set will adapt to whatever size the dimensionality of that video is. And here's how it does it. This subpatcher has an object called jit.matrixinfo that gives you all kinds of useful information. Let's just print it out. Print. Max console. Oh boy. Much information. So it's telling us the plane count, the dimensionality, and the data type. And then this object, root, is going to send those messages to different outlets when they match in different ways. So this is the outlet for input that starts with the message plane count. This is going to be if it starts with type, and this is going to be if it starts with DIM. Those are the 3 arguments we've given to root. So there is our plane count. It's 4. This is going to be our data type, which is char. And then this is going to be the list, that is the dimensions of this video. So this video is 320 by 240. ZL dot change is another flavor of the ZL object that only outputs the list when the value has changed. So I'm running it through ZL change so that we're not constantly changing the size of our matrix set. We only do this once when we get a new resolution. And then we're using send and receive. So we receive that list over here, and we're using this message to change the dimensions of the matrix set. Okay, quick diversion. We've got all these messages in these patches that have these dollar signs and numbers inside of them. So let's just quickly review what they do. So here's just a normal message. It's got a list with these two words in it. Oh, this is still printing. Stop printing, friend. Okay. Here we go. Here we go. Yes. We're printing hello world. You could break it with a comma. It would become two messages. Sweet. You could add some integers to this. And now it says hello world 1, 2, 3, 4. If we want to change elements of this message, we can do this using these special parts of the message, $1, $2, $3, $4. These create kind of like variables where we can change the value. And we do that by sending it just any other type of message. So here we can send it some floating point numbers. And $1 is getting replaced by this floating point number. We could send it another message. Like here, we'll send it the word there. And the $1 gets replaced with that message there. Hello there, 1, 2, 3, 4. And we could have multiple such things. We could have $1, $2. And this is going to look for the first element of an incoming list and then the second element of an incoming list. So if we sent it this list consists of two things, there and beautiful. So $1 is going to get replaced with the first part of this message, and $2 is going to get replaced with the second part. So we print out hello there, a beautiful world. You could reverse the order if you wanted to. So we'll look up the second element and then the first there, and it says hello, beautiful there, world. We could send it a floating point number, and $1 is getting replaced by the first element of this floating point number. So these $sign and then a number that you'll see in a message box are a handy way to create a message where you can replace certain parts of it with incoming elements of a list, or just individual things like floating point numbers and integers and so forth. Okay, so coming back to this patch, we've got these three messages. They all have these special dollar messages, and we know now that this is giving us replaceable parts of this message. So here we're getting index and then this integer. This is giving us $1, $2. This will get replaced by whatever list comes from here, and that is going to be the size of our video. That's a list with the horizontal and vertical resolution. And this $1 gives us whatever number we get from here, which is our delay line. Loop, play, great. Okay, so that gives us the delayed signal, just as we saw before. And to create an echo effect where the current version of the signal is being simultaneously displayed with the delayed version, we need to explicitly add together these two matrices, as we saw a couple patches ago. So here we are again using jit.expr with a specific expression that combines these two matrices. This is what's coming from the camera, and this is our delayed signal. And then we just output that into jit.world, which is being displayed in this floating window here. Okay, great. So that's basically how you create a video echo effect. Again, we're using matrix set to create this buffer, and then we are accessing different parts of this buffer using this counter that's just looping around inside the range of the buffer, and we are adding together the original and delayed signal using this expression. Boop, boop, boopity boop. Okay. So now adding feedback to a video delay line. Here is a delay patch, much like the ones we've just been looking at. We're going to, again, just play a QuickTime movie in a loop. We can use this number to set the delay time. So we've got our counter that's counting backwards. We're indexing around. We're outputting frames. So we know this is going to give us a delayed version of the video signal. But the difference here is that the input that we're putting into this delay line, it's not the camera signal in this case. The input is the output of our delay line, which is mixed with the camera signal. So our camera signal in this patch goes down here where we add it together with the delay line. And then the result is sent here. So we get a matrix with some random looking name like this. And then up here, we receive that message. This is the output of our delay line, and it goes back into the delay line. And what we get as a result is a video echo that propagates for a certain amount of time based on a feedback coefficient, which in this case is written here. So our expression is scaling one input in of 0 by this amount, 0.45, and the other one by this amount, 0.55. So this is our feedback coefficient in this expression. If we wanted much more feedback, we could increase this coefficient. And if we want to prevent it from oversaturating the screen, we would probably want to decrease the other one. And you'll see that the delays are really propagating for a long time on the screen when we do this. We could switch to some other video, and I think you would still see this first one playing for quite some amount of time. So we're playing the ducks video, but it takes a while for the first one to disappear. It's a short video. Oh boy, so crazy looking. Much feedback. Very melty. Wow. Okay, so that is a video delay line where we're using feedback by sending the output of the delay line back into it, and we're scaling it by these coefficients down here. Now let's look at this idea of adding another processor into a system like this to create cascading effects. So here again is a delay line. Again, we are time shifting it in the same way as the previous patch. We're just doing one more thing. We're taking the output of the time shifted signal and we're running it through this thing, which is just a rotator. This is actually an example of a Visi patch. Visi patches are these kind of like ready-made processors. I don't really teach these because they're sort of designed to be used by beginners without knowing how they work. So don't worry about how this works. But it does take a floating point number, which is going to change the rotation. And I'm driving that floating point number using this, which is part of the jit.mo package. So this is creating a kind of like LFO that's going up and down in this range of 1 to -1, and this is rotating our signal. So we're creating a time-shifted version of the video signal. We're using feedback, and the feedback is now, the output has also been rotated. So we're rotating a rotated version. So we're starting to get these cascading effects. And again, our feedback coefficient is this number. So if we want more feedback, we could make this a larger number. Wow, and this kid is wearing some like white socks, and those white socks are like turning into rainbows because of all the feedback inside this system. Super. Do I want to save this? Sure. Close. Okay. One last thing I'm going to show you. So this is just an example of some crazy stuff that you can do using these basic ideas. This is a patch I made that will generate infinite video feedback, meaning any signal that gets put into it will propagate forever. So, you know, if you are enrolled in this course and you carefully read the syllabus, which you should have, you would have seen a link to this as an example of how to document your video work. This is a video I made. This is me writing the syllabus for this very class many years ago, when back when I was still a youthful and vigorous individual. My hair was a lot shorter. So apparently I wrote the original syllabus for this class in 26 minutes. So at the beginning of this video, I'm looking at my computer screen. I've got short hair. I'm a very young person. I drink this glass of water. And now we're seeing a delayed version of this signal. And from this point onwards, everything I do in the video will echo forever, because I'm carefully scaling the amount of the delayed signal that gets added back in. All right, so let's look at a live demo. Here we go. Let's switch this to the camera. It's me. And let's click the reset button. So the patch is going to start by showing me a delayed version of the camera signal. And every gesture I make is going to be added to this network of delayed video signals, and it will propagate forever. So this is my patch with infinite feedback. The way this works is every time this counter wraps down to 0, we use a select object which increments this counter, and then the counter is carefully changing the feed forward and feedback coefficients using these two floating point numbers. So if any of you are music producers, maybe you're familiar with this idea of like a dry-wet parameter, where dry is your kind of original signal and wet is your processed signal. These are you could think of this as the dry-wet mix for my video delay, where this is the dry, the original signal, and then this is the level of feedback that's being applied to the video delay line. So the level of feedback is increasing. So the expression for this patch looks like this. We've got in of 0 and in of 1, but our feed forward and feedback coefficients are being updated using two other inputs, this one and this one. And to make that work, I also have to explicitly tell jit.expr that this instantiation of the object has 4 inputs. And then we just take the output of this delay line and display it on this jit.world. So there we go. I pretty quickly melted my own face. Because I'm mostly just standing in the middle of the camera, you can see me mostly standing there, but you can see a little bit of the arm gestures I've been doing. These like ghosty traces of my arms. Okay, there you have it. That is creating patches in Max that do time shifting of an audio signal and time shifting of a video signal, and then adding feedback into that, adding other forms of processing to do cascading effects, and then doing some clever mathy things to create really weird effects like this one, our video delay line with infinite feedback. Thank you for joining us. That's all we got for you. We'll see you next time.